Picture a mountain of jet black rock. It sits on the edge of a dusty city stretching to the horizon. It smells faintly of sulfur. Nothing grows on it. For decades, the locals view this pile as a permanent scar, the toxic, useless leftovers of a coal mine, a monument to waste. You would expect the local government to bury it, to hide it behind a tall concrete wall. Instead, a team of structural engineers is standing at the base, scooping the black rubble into sample bags. They aren't planning a cleanup. They are looking at this toxic heap and seeing the pristine white pillars of a future high-rise. It feels like a glitch in basic logic. We live on a planet covered in deserts. We have dunes that swallow entire highways. We have beaches that map the edge of every continent. Yet the people tasked with holding up the modern world are walking right past the endless golden sand to harvest a pile of black soot. When the fastest building nation in human history started looking at its garbage to keep its rooftops from caving in, it isn't a quiet green initiative. It's a quiet panic, and leaves us staring at the ground beneath our feet, forced to ask a very strange question. How do you run out of the earth?
It's a completely surreal situation, really.
It is. And to really understand how we got here, I want to take you to a soundproof control booth, sitting high up in a limestone quarry in Guizhou.
Oh, okay.
All right, so inside this booth is a man named Old Master Lao. And for 40 years, Lao's entire livelihood involved judging the fatness of the Yangtze River's belly.
The fatness, like the quality of the sand.
Exactly. He did this by literally feeling the grit of wet river sand stuck under his thumbnails.
Yeah.
He knew the riverbed intimately, you know?
Yeah.
But now his old dredging boat has been chopped up for firewood.
Oh, wow. So his entire way of life is just gone.
Completely gone. And he is standing in this pristine control room, holding a pair of neon orange earmuffs that he stubbornly refuses to put on, and he's staring out at a totally different landscape.
Yeah, a quarry is a very different beast from a river.
Right. And beside him stands Joseph. Joseph is a 24-year-old junior engineer who was sent all the way from the Ministry of Roads in Nairobi, Kenya.
Okay, that's quite a trip. What's he doing there?
He's there to learn a very specific recipe. Through the double-paned glass in front of him, there is a primary jaw crusher. And you have to imagine the sheer violence of this machine.
Oh, those crushers are, they're terrifyingly powerful.
In 4 seconds, it chews a 3-ton boulder into gray flour. The acoustic impact, even through the glass, sounds like a dry femur snapping inside a megaphone.
That's a vivid image and incredibly loud, even with the soundproofing.
Totally deafening. So Lao mutters in his local dialect. He is holding a dry sample of what they call jizisha.
A manufactured sand.
Exactly, the stuff that just came off the test belt. He rubs it with his calloused thumb, complaining that it's just too angular. River sand, he says, has been rolled by the Dragon King for 10,000 years.
Well, yeah, it's perfectly round.
Right, it yields to the trowel. But this machine-crushed rock, Lao says it fights back. He notes that it drinks the cement's water far too fast.
And, that tactile feedback Lao is experiencing, that is the physical manifestation of a massive geological pivot. Well, for the entirety of human history, our built environment relied on geology doing the slow, patient work for us, right? Water erosion over millennia produced the perfect building material.
Just naturally tumbling the stones until they're smooth.
But waiting 10,000 years for a river to tumble a rock into a sphere, it's just no longer a viable timeline for modern urbanization. We are building too fast.
Which brings us back to Joseph. He doesn't speak Lao's dialect, but he completely understands the thumb movement.
Because the physics of concrete are universal.
So Joseph pulls up a digital slide on his tablet. He shows Lao the sun-bleached, cracked riverbeds of the Machakos Hills back in Kenya.
Oh, I've seen images like this. It's devastating.
The image shows a landscape stripped down to the raw bedrock by illegal sand cartels. Joseph explains, in slow English, pointing at the roaring mechanical cone of the crusher, that in his home province, young men are actually killing each other with machetes over a 5-ton tipper of that smooth river sand.
That really puts the scale of the global demand into perspective. It's a matter of life and death.
And he looks at Lao and says, "We do not need the mortar to be polite to the trowel. We just need the primary schools to stop collapsing when the long rains arrive."
It functioned over form completely.
Right, so Lao looks at the screen, looks at the gray dust on his own tea thermos, and he reaches into his jacket. He pulls out a single, perfectly smooth, pea-sized quartz pebble he saved from the great floods of '98.
Like a souvenir from his past life.
Exactly. He sets it on the console, turns the master feed dial up, and tells Joseph to increase the superplasticizer by 0.2%. And his final piece of advice to the young engineer is to stop looking for the river, Because the mountain is the river now.
The mountain is the river.
It's a complete shift in reality. But, before we go any further into how we are crushing mountains, we have to address the immediate glaring paradox here in this deep dive.
The desert sand issue.
If you look at a globe, the planet is completely coated in sand. We have extending deserts, we have the Sahara, the Mojave, the Gobi. The wind blows sand across entire oceans.
It seems like we have an infinite supply, right?
How is it physically possible that humanity is experiencing a sand crisis when there's so much of it just sitting there?
Well, the answer lies entirely in the microscopic geometry of the grain. To understand this, you really have to look at the physical mechanics of how concrete actually cures and holds weight.
Because concrete is just dried mud.
It is not just dried mud. It is a highly complex artificial rock. It relies on a chemical matrix made of cement powder, water, and aggregates.
And the aggregates are the sand and gravel.
The cement and water form a paste that coats every single grain of sand. But for that final structure to possess any actual compressive strength, like for it to be able to hold up a 40-story building, the individual grains of sand need to physically interlock.
Like puzzle pieces.
They need sharp, jagged, violent edges that can grip onto one another tightly when the chemical paste hardens around them.
So if you take a handful of sand from the Sahara Desert and try to use it, what actually happens?
You are essentially trying to build a skyscraper out of microscopic ball bearings.
Ball bearings.
Desert sand is shaped by aeolian processes, meaning it is shaped by wind.
Okay.
For millions of years, the wind whips across the dunes, causing the sand grains to violently collide with each other in the open air. This constant aerial abrasion effectively polishes every single grain.
So there are no sharp edges left.
If you put a grain of desert sand under an electron microscope, it looks like a perfectly smooth, round little glass marble.
Oh.
And if you mix 1 billion tiny glass marbles into wet cement paste, there is zero friction. The grains just slide right past each other.
So a concrete column made with that wind-polished sand.
It has no internal matrix, no interlocking grip, and it will simply crumble under its own weight.
That paints a very clear picture. You absolutely need the jagged geometry that comes from rocks being tumbled in water, or, as in Lau's case, rocks being violently sheared apart by steel jaws.
Right, the manufactured sand provides those crucial jagged edges.
Earlier, Lau mentioned something highly specific to Joseph. He told him to increase the superplasticizer by 0.2% because the crushed rock was drinking the water too fast.
Yeah, that's a vital part of the process.
What exactly is a superplasticizer doing in this chemical matrix? Why not just add more water if the rock is thirsty?
Well, a superplasticizer is a critical chemical admixture, and understanding it is key to understanding how manufactured sand even works at scale. As Lau noted, machine-crushed sand is highly angular and rough.
Because of the violent crushing process.
And because of all those tiny jagged edges and microfractures, it has a vastly larger surface area than smooth river sand.
So more surface area means more area for the water to cling to.
Exactly. When you mix it with cement, that massive surface area acts like a sponge, absorbing the water very quickly. Now, as you said, the instinct might be to just add more water to make the concrete flow better so it can be poured.
Right, because you need it to be liquid enough to pour into the molds.
But in concrete chemistry, the water to cement ratio is the absolute dictator of structural strength. If you add too much water, the concrete becomes weak, porous, and incredibly prone to cracking.
So you are trapped between needing the wet concrete to flow easily into a mold, but not being able to add the water necessary to make it flow.
You're in a chemical catch-22. And this is where the superplasticizer comes in.
What is it?
It is a synthetic polymer. When you add just a tiny fraction of a % of this liquid to the mix, the polymer molecules wrap themselves around the cement particles.
Like coating them.
And these molecules carry a strong negative electrical charge.
Okay, tracking with you.
Because all the cement particles are now coated in this negative charge, they physically repel each other.
Oh, like taking two negative ends of a magnet and trying to push them together.
This electrostatic repulsion allows the concrete to flow smoothly like a liquid without needing to add a single extra drop of water.
That is a brilliant piece of chemical engineering.
It allows engineers to use rough, thirsty, manufactured sand while maintaining the exact chemical ratios required for maximum structural integrity.
But even with the right chemicals, the physical scale of the rock we are grinding up is just difficult to comprehend.
The global metric for extraction is completely staggering. Humanity extracts 50 billion tons of sand and gravel every single year.
50 billion tons. I mean, the human brain is not wired to visualize a billion of anything.
And so consider the physical volume. 50 billion tons is enough raw material to construct a solid wall around the entire equator of the Earth.
Wow, how big of a wall?
A wall measuring 27 meters high and 27 meters wide.
Around the entire equator.
And we are harvesting that exact volume every 12 months. It is the second most consumed resource on the planet after water.
Staggering. And to really understand where this massive volume is going, you have to look at the timeline of human urbanization, specifically the comparison between the United States and China.
Right. The historical data really highlights the acceleration.
Yeah, if you track it, it took the United States roughly 70 years, spanning from 1880 to 1950, to transition its population from 30% urban to 66% urban.
And that period was a massive building boom.
That is the era that saw the construction of the Hoover Dam, the expansion of the interstate highways, and the raising of the skylines in New York, Chicago, and Detroit.
Yeah.
It was a massive generational effort.
Now, overlay that exact timeline onto China's development.
Okay.
It took China the exact same duration, a 70-year window from 1949 to 2020, to hit that exact same urbanization milestone, moving from an agrarian society to a heavily urbanized one. A huge one. The crucial difference is the demographic multiplier. China executed this shift with a vastly larger population.
And the numbers attached to that demographic multiplier are what force you to just completely recalibrate your understanding of heavy infrastructure.
The concrete statistics are mind-blowing.
In a single 3-year period, China poured 6.6 billion tons of concrete.
Just 3 years.
3 years. And to anchor that in reality, the United States poured 4.5 billion tons of concrete in the entire 20th century.
So 100 years of relentless American empire building was statistically eclipsed in 36 months.
And when you are pouring 6.6 billion tons of concrete in a 3-year window, you immediately collide with the physical limits of the Earth's natural geology.
You physically cannot dredge enough riverbeds to supply the sand required for that volume.
If you tried, you would systematically dismantle the ecology of every major waterway on the continent.
Riverbanks would collapse, water tables would plummet, and the foundational supports of existing bridges would be literally vacuumed away by dredging ships.
Which is exactly what began happening and what necessitated an incredibly rapid top-down policy intervention.
The data on this shift is fascinating.
If we look at the material flow analysis data tracking China's sand supply from 1995 to 2020, you see a nation pivoting its literal foundation.
What were the numbers in the 90s?
Well, in 1995, natural sand dredged from rivers and lakes accounted for roughly 80% of the total supply. The volume at that time was about 1.4 billion tons a year.
Okay, manageable on a national scale.
But fast forward to 2020, the total supply requirement surged by 400% to 7.0 billion tons annually. However, the composition inverted. Natural sand dropped to just 21% of the supply. Manufactured sand, which is mountains reduced to dust by machines, surged to dominate the market at nearly 80%.
And that inversion was not a slow organic market adjustment. It was a result of a highly coordinated top-down environmental mandate.
Because they saw the rivers dying.
By 2010, the central government recognized that the ecological devastation of the rivers was completely unsustainable. So they initiated sweeping, strict regulations on natural sand mining.
But you cannot simply ban a resource that your entire economy relies upon without providing an alternative, right?
No, the economy would collapse. So the following year, in 2011, they updated the National Construction Sand Standard, known specifically as GBT 14684.
What did that update actually do?
This legal standard was completely rewritten to forcefully promote the integration of manufactured sand. It provided the strict engineering frameworks and chemical guidelines, like the precise use of those superplasticizers we discussed, to ensure that crushed rock could legally and structurally replace river sand in all high-level construction.
And the ultimate enforcement mechanism for this arrived a few years later in 2016 with the implementation of the River Chief system.
The River Chief system was the definitive clampdown.
How did it work?
It assigned specific, named government officials direct personal responsibility for the ecological health of specific waterways.
Oh, so if a river gets destroyed, they know exactly who to blame.
It criminalized the destruction of riverbeds and functionally eliminated large-scale, unregulated natural sand dredging. It was a decisive policy success that forced the entire construction industry to adapt instantly. If you couldn't scrape the river for your raw materials, you had no choice but to build massive crushing facilities and start carving up the mountains.
Which circles perfectly back to Joseph standing in that Gizou control booth. The realization that as the rest of the global south, across Africa, Asia, and South America, prepares to urbanize another billion people over the next 2 decades,
Yeah.
they are going to have to adopt this exact model.
Right, because their rivers are already depleted, too.
The world has to learn how to expertly crush the mountain. But, as you look at the timeline, even mountains have limits.
Manufactured sand solved the immediate ecological crisis of the dying rivers, but it requires immense energy.
And you are still extracting virgin rock from the earth. You are still carving permanent voids into the landscape. And eventually, a city built from crushed mountains begins to age.
Which brings up the next major phase of this transition.
Right. So to explore that, I want to introduce you to an excavator operator named Chen.
Okay, where is Chen working?
For 12 years, Chen's entire professional life in the northern industrial city of Shijiazhuang had been dedicated to making things disappear. He operates a massive 36-ton excavator, which basically acts as a great yellow eraser across the city's old textile district.
So he's in demolition.
He is used to dropping the heavy iron ball on 1980s red brick worker dormitories, burying the rubble and moving on. But recently, a new municipal mandate called Circular 2050 was issued to all the subcontractors.
And what does Circular 2050 mandate?
It dictates that machines are no longer allowed to just bite into a building and throw the corpses away, so to speak. Now they are required to digest. So Chen is sitting in the cab of his mobile crushing crawler, parked directly over the footprint of an old communal kitchen. Down into the steel hopper goes the load-bearing rubble.
Right into the crusher.
Yeah. And among the debris is a chunk of a pale green concrete windowsill. This was the exact sill where his old neighbor used to set her salted cabbages to dry in the wind.
Wow. Very personal.
Yeah, lots of history there. As it falls into the primary rotor, there is a high-pitched, agonizing shriek of metal on metal. Chen slams the red emergency kill switch.
Something jammed the machine.
The silence rushes back into the dust cloud, smelling faintly of 40 years of trapped pork fat, lime plaster, and damp soot. He climbs down out of the cab with a 3-foot crowbar to clear the machine's throat. Wedged between the steel crushing teeth is a bent, rusted segment of rebar wrapped tightly in a dense knot of gray aggregate. And stuck to the side of that stone is a tiny, indestructible scrap of a 1997 wall calendar showing a bold red numeral 14.
It's incredible how those tiny pieces of daily life survive the demolition.
But he doesn't have time to dwell on it. His radio crackles. The site manager tells him to hurry up because batching plant 3 needs 40 tons of grade 2 recycled coarse aggregate by sunset.
They need it for a new project immediately.
Yeah, for the sub-base of a new ring road extension. So Chen wedges his iron bar under the rusted rebar, throws his entire body weight against it, and dislodges the jam with a wet, hollow pop.
Getting the machine running again.
He doesn't keep the calendar scrap. He steps back and watches it flutter down into the dark teeth as the diesel generator roars back to life. And within 24 hours, the pulverized dust of that pale green windowsill will be pumped 300 feet into the hazy sky, poured cold into the central load-bearing core of a new 40-story financial tower.
That visceral on-site transition from knocking a building down and hauling it to a landfill to literally digesting it where it stands and pumping it back into the sky is the operational foundation of an amazing new framework.
What framework is that?
It was developed by researchers at Tsinghua University. It is called the CHAMPS model, which stands for the China Aggregate Metabolism Provincial Scenarios.
Metabolism. That really leans into the idea of digesting the city.
It is a highly sophisticated predictive model that maps the supply, flow, and usage of aggregates across every single province.
What's the end goal of CHAMPS?
The objective is to transition a rapidly developing nation entirely away from a linear economy.
A linear economy being what we've always done.
Right. You extract raw rock, you build something, you tear it down, and you bury the waste in a landfill. That's a line. The CHAMPS model maps out a massive circular economy where the existing, aging, mid-century cities themselves become the primary quarries for the future.
I have to pause here, though, because there's a serious physical hurdle that comes to mind when you envision crushing up an old building to make a new one.
The structural integrity issue?
We just established earlier that concrete is a highly precise chemical matrix. You take virgin rock, you coat it in cement paste, and it undergoes hydration to harden. Once that chemical reaction is finished, the rock is permanently glued. So how is it possible to take a chunk of a 40-year-old concrete windowsill, run it through the violent steel teeth of Chen's machine, and use that shattered material to pour the load-bearing core of a 40-story financial tower?
It seems like it shouldn't work.
Doesn't the act of crushing the old concrete destroy the structural integrity of the stone? You can't just infinitely crush and re-glue the exact same rocks without losing strength, can you?
The physics you are questioning is exactly what makes the engineering behind the Champus model so advanced. You are entirely correct that recycled construction and demolition waste, often referred to as CDW in the industry, is not structurally identical to virgin crushed mountain rock.
So what's the difference at a microscopic level?
When Chen's machine crushes that pale green windowsill, the resulting pebbles are not clean. They are what engineers call composite aggregates.
Meaning they're a mix of things.
Yeah. Every piece of original rock still has a thick layer of old, hardened cement mortar permanently glued to its surface.
And I imagine that old mortar changes how the rock behaves when you try to mix it into new wet cement.
It changes it. That old mortar is highly porous. It is full of microscopic voids.
Kind of like the manufactured sand drinking water too fast.
When you introduce recycled CDW into a new batch of concrete, that old porous mortar acts like a severe sponge, aggressively sucking the moisture out of the new cement paste. This disrupts the hydration process.
That sounds like a big problem.
But more critically, there is a mechanical weakness known as the interfacial transition zone, or the ITZ.
Okay, what exactly is happening in the ITZ?
The ITZ is the microscopic boundary layer where the cement paste meets the surface of the aggregate.
Like the glue line.
Exactly. In normal concrete, you have one ITZ between the new cement and the virgin rock. But with recycled aggregate, you have multiple transition zones.
Because of the old mortar.
You have the boundary between the original rock and the old mortar, and then a completely new boundary between the old mortar and the new cement.
So you've doubled the weak points.
These boundaries are the weakest links in the entire matrix. They're highly prone to microcracking.
So if you blindly grind up an entire apartment building and use 100% of that unrefined dust to pour a skyscraper foundation,
the multiple weak transition zones would cause a catastrophic structural failure under heavy load. The building would simply fail.
So how do you solve the ITZ problem? How are they safely using this material to hold up the financial towers of tomorrow if it's inherently compromised?
The solution lies in incredibly precise sorting, grading, and application technologies. When Chen's mobile crawler crushes the rubble, it isn't just making a random pile of powder.
What happens to the rubble?
The material immediately enters a highly mechanized sorting line right there on site. First, it passes under massive magnetic separators.
It's rid of the metal.
Right. These are powerful electromagnetic belts that physically rip all the old rebar screws and iron ties out of the crushed rock.
That handles the metal, but what about the lighter junk?
Then, the material passes through what are called air classifiers.
How do air classifiers differentiate between rock and waste?
They utilize the physics of fluid dynamics and terminal velocity. Inside the classifier, powerful upward streams of air are blown through the falling crushed material.
So the heavy stuff drops and the light stuff fly.
Dense, heavy materials like the high-quality concrete chunks and solid rock fall straight through the air current. But lighter materials like pulverized drywall, splinters of wood, plastic conduit, and loose dust are caught by the airstream and blown away into separate collection bins.
You use air pressure to physically separate the wheat from the chaff based on density.
Once you have isolated the pure, heavy aggregate, it is mechanically screened into different grades. You remember the site manager on Chen's radio?
Yeah, he specifically asked for grade 2 recycled coarse.
In the national standards, recycled aggregates are classified based on their density, their water absorption rates, and their crushing value.
So what's grade 1?
Grade 1 is the highest quality. It's heavily processed, very dense, with most of that problematic old mortar stripped away entirely. Grade 2 has more old mortar attached and is a bit more porous, and grade 3 is lower quality still.
And because they have graded it so meticulously, they know exactly where it is mathematically safe to use it.
They utilize a blended application method. An engineer might prescribe a mix containing only 10% to 15% of grade I recycled aggregate for the critical high-load columns of a skyscraper, filling the rest out with virgin manufactured sand.
So the really important parts are still mostly new rock.
But for the subbase of a new ring road, or for non-load-bearing partition walls or pedestrian paving stones, they can safely use 50% or even 80% of grade 2 and grade 3 materials.
It is a meticulous, citywide metabolic management system. They map the exact nutritional breakdown of a demolished neighborhood and feed it back into the construction grid precisely where it fits best.
It's incredible logistics. And when you look at the projections generated by the Tsinghua researchers mapping this metabolism, the sheer scale of the circular economy they are building is mind-bending.
What do the projections look like?
The future trajectory outlined in the Chambas model is incredibly clear. The projections show that China's overall annual demand for aggregates will naturally halve by 2050.
Because they'll be done building the majority of their major cities.
The bulk of their major urbanization phase will be complete, so demand drops down to roughly between 9.2 and 12.4 billion tons a year.
Okay, wait. Even having the demand leaves an astronomical number.
Yeah.
12 billion tons is still the equivalent of constructing 1,500 Great Pyramids of Giza every single year.
It is a massive baseline. But here is the critical breakthrough in the model. By fully implementing these advanced magnetic and air classification recycling technologies, by legally extending the required lifespans of existing buildings, and by adopting advanced, lightweight architectural design, recycled City W will be capable of meeting 48% of that total national demand by 2050.
Nearly half.
Nearly half.
Almost half of every road, bridge, and skyscraper built in 2050 will be comprised of the chewed-up, digested remains of the structures that stood there before.
And the data gives us a specific timeline for when this physical tipping point occurs. The model projects that the total volume of recycled aggregates will physically surpass the volume of newly manufactured, mountain-crushed aggregates by the year 2046.
So the lines cross in 2046.
And that is just the blended national average. In highly advanced, heavily regulated regions, provincial governments are targeting aggregate recycling rates as high as 65%.
It is the ultimate logistical evolution forced by the physical limits of extraction. First, the industry dredged the rivers until the banks collapsed, prompting a total ban. Then they brought in the heavy machinery and blasted the mountains until the sheer environmental and energy costs of continuous quarrying became untenable.
The mountains aren't infinite either.
Exactly. Finally, they realized that the absolute densest concentration of ready-made building material isn't hiding inside a mountain or a riverbed. It is standing right in front of them, in the form of a sprawling 40-year-old factory complex.
The city transforms into a self-contained, rotating inventory of mass.
Digesting the city solves two massive logistical nightmares with a single industrial process. It drastically reduces the need for destructive quarrying that permanently degrades landscapes, and it simultaneously eliminates the spatial crisis of trying to find landfill space for billions of tons of demolition waste.
It's a win-win on a colossal scale.
Recycling old concrete makes incredible sense. You're taking old rock, scrubbing it, and turning it back into rock. But this brings us to a much darker, almost sci-fi level of material alchemy. What happens when the material you desperately need to eliminate from your landscape isn't just old, inert concrete? What happens when the waste is actively toxic, highly combustible, and leaching poison into the groundwater?
That's a completely different level of challenge.
And to explore this, we need to look at a geographical feature in Datong, Shaanxi province, known as the Black Hump.
The Black Hump.
The Black Hump had sat on the northern horizon for so many generations that the provincial cartographers had actually shaded it in on maps as a natural spur of the local mountain ridge.
But it wasn't natural at all.
Every vertical inch of its 300-foot rise was artificial. It was a massive pile of vomited, unburnable shale pulled from the No. 3 state colliery.
A coal mine waste pile.
Right. And when the July monsoons hit Datong, the mountain bled. It leashed a bright, toxic ochre runoff directly into the suburban cabbage plots. In the autumn, when the dry winds swept across the plains, the pressure inside the pile would cause it to spontaneously catch fire.
Just burst into flames.
It burned with a low, invisible heat, smelling of rotten eggs, wet matches, and old funerals.
It sounds like something out of a dystopian novel.
I want to introduce you to a woman named Ma Lan. When she was a teenager, Ma Lan used to spend her harsh winters illegally picking through the frozen skirts of this toxic mountain, searching for missed nubs of actual coal, just to keep her grandfather's toes from turning black with frostbite.
So she grew up in the shadow of this thing.
And now, at 52 years old, she is standing inside a gleaming facility built right next to the hump. She's wearing a static-free, sterile white smock. And she is watching a robotic titration arm extract liquid gallium from a bubbling vat of dissolved rock.
Liquid gallium, that's a huge leap from picking coal.
Through the double quartz window of a massive rotary kiln, the toxic shale from the mountain is being roasted at 1,200 degrees Celsius alongside industrial fly ash. The extreme heat is driving the heavy metals out of the rock into magnetic capture flues.
So they're literally cooking the toxins out.
The pitch-black sulfurous curse rock is being transformed, emerging from the kiln as a steady, chattering stream of pale, honeycombed, lightweight ceramsite pebbles.
It's an incredible metamorphosis.
Mala's older brother had actually died of black lung in the third shaft of that very colliery back in the winter of '04. He used to spit at the hump and say, "The beast eats the meat and leaves us the bones to look at."
Ow.
So Malaland scoops a freshly cooled handful of the synthetic aggregate out of the collection bin. It is stark white. It feels almost weightless in her palm, like calcified sea foam.
Completely different from the heavy black rock it started as.
And beside her is a 26-year-old technician from Ningbo, a young man with soft hands and a master's degree in inorganic chemistry. He is excitedly tapping the screen of his diagnostic pad, pointing out the closed-pore ratio to Malan.
The closed-pore ratio.
Yeah. He explained that if they cast the northern municipal perimeter wall with this specific batch of pebbles, the internal thermal resistance will drop the district's winter heating grid load by 7%.
Because it insulates so well.
He calls it a 20-kilometer stone thermos. So, Malan brings the white pebble slowly to her nose. She closes her eyes, expecting to catch the phantom, suffocating reek of the damp underground staging areas. The bitter bite of raw sulfur.
But there's no smell, right?
Nothing. It is completely terrifyingly odorless. It has been scrubbed of its history, quantified, certified, and rendered entirely innocent. She drops the little white bone back into the steel trough and says, "It's going to make a very warm wall."
And the scale of the scar that coal gang has left on the landscape is difficult to overstate.
What exactly is coal gang?
Coal gang is the solid waste byproduct generated during coal mining and coal washing. It is the tough, unburnable, mineral-rich rock that gets hauled out of the earth alongside the valuable coal. And historically, it accounts for more than 10% of total coal production.
So wait, for every 10 tons of coal you burn to power a city, you are left with 1 ton of this toxic rock just sitting on the surface.
And because China has historically relied on coal to fuel its unprecedented rapid industrialization, the accumulation is vast. There are currently over 7 billion tons of coal gang piled up across the country.
7 billion tons.
And the mining industry generates another 500 million tons every single year. These massive black humps are literal ecological time bombs.
Why are they so dangerous, though? Why do they spontaneously catch fire, and why do they leach that toxic ochre into the cabbage plots like in Datong?
It comes down to the mineral composition of the gang, specifically the presence of iron sulfide, which is commonly known as pyrite.
Like fool's gold.
When billions of tons of gang are piled up and exposed to oxygen and rainwater, the pyrite undergoes a chemical reaction called oxidation.
Okay, and what does oxidation do?
This oxidation process is highly exothermic, meaning it generates a massive amount of internal heat. Deep inside these mountains of rock, the heat builds up until the residual carbon in the shale reaches its ignition point.
And that's what causes the spontaneous combustion.
And when it burns, it releases massive plumes of sulfur dioxide and toxic smoke. Simultaneously, the oxidation of pyrite produces sulfuric acid.
Oh man, so it's making acid internally.
And when it rains, this acid washes down through the pile, dissolving heavy metals like lead, arsenic, and cadmium out of the rock and carrying them directly into the soil and the local water tables.
That is just a nightmare. You have 7 billion tons of toxic, flammable, heavy metal-laced, acid-bleeding rock. And an engineering team looks at that and decides they're going to build houses out of it. It sounds like absolute madness. It is an industrial exorcism. You are taking a cursed liability and attempting to literally burn the devil out of it.
But that is the exact mission of the Daitong demonstration project. It is a landmark 10 million ton facility dedicated entirely to processing coal gang into high-value building materials. It operates on a highly specific technical framework known as the 1267 concept.
Let's break down this 1267 blueprint, because it outlines how you achieve this atomic-level transfiguration. This is far beyond just grinding up rocks.
The 1267 blueprint maps the entire industrial flow. The 1 stands for one massive integrated crushing and screening plant where the raw gang is initially broken down.
Okay, so step 1 is crushing. What's the 2?
The 2 represents 2 advanced photovoltaic sorters. The 6 stands for 6 key cutting-edge thermal and chemical operations. And the 7 stands for the 7 high-value outputs that are generated at the end of the line.
Let's zoom in on the 2, the photovoltaic sorters. How do you use light sensors to differentiate between a piece of toxic shale and a piece of useful rock when they're all tumbling down a conveyor belt at high speed?
The technology relies on hyperspectral imaging. Traditional cameras just see visible light, but hyperspectral sensors capture information from across the electromagnetic spectrum.
So they see invisible light.
Right. And every mineral reflects light differently. Pyrite reflects light at a different wavelength than quartz or clay.
Okay, so the computer can identify what's what based on the light signature.
Exactly. As the crushed gangue flies off the end of a high-speed conveyor belt, these sensors scan the rocks in midair.
In midair.
In a fraction of a millisecond, the computer analyzes the light signature of every single pebble. If it detects a piece of rock with too high a concentration of sulfur or unwanted minerals, it triggers a row of pneumatic air valves.
And what do the air valves do?
A targeted blast of high-pressure air shoots that specific toxic rock out of the midair stream and into a separate waste bin.
You are literally sorting toxic rocks in midair using light waves and air jets.
It's incredibly fast and precise.
Okay, but once you have sorted the optimal material, how do you actually purge the remaining poison? How do you get from a piece of black gangue to the odorless white ceramsite pebble Milan was holding?
This is where the 6 key operations come into play, primarily relying on extreme heat and advanced filtration. Inside those massive rotary kilns you mentioned earlier, the sorted gangue is blended with industrial fly ash and roasted at 1200 degrees Celsius.
That is incredibly hot.
To handle this immense thermal load at scale, they actually borrowed a continuous belt firing method directly from the steelmaking industry. The extreme heat effectively sweats out the toxins. The volatile compounds and sulfur are simply vaporized.
But heavy metals don't just vaporize, do they? How do they handle the iron and the other dangerous elements locked deep inside the stone?
For that, they utilize a unique X-ray transmission and electromagnetic wave cleaning system.
X-rays, like in a hospital.
Before and during the thermal processes, X-rays penetrate the rocks. X-rays are highly sensitive to atomic density. Heavy metals have a much higher atomic density than the surrounding silicate rock.
So the X-rays spot the heavy metals.
The X-ray system maps exactly where the heavy metal concentrations are, and then powerful electromagnetic separators are used to effectively strip out the iron and other magnetic impurities.
And the incredible part is that they aren't just throwing those extracted heavy metals away. The engineers are actively recovering trace amounts of critical, high-value rare earth elements during this purging process. They are pulling out elements like lithium, germanium, and liquid gallium,
which are extremely valuable.
These are the exact metals required for global tech supply chains, for manufacturing microchips and batteries. The process financially supports itself by harvesting these highly sought-after elements before the final building material is even formed.
It completely flips the economic model. You extract the valuable tech metals, you magnetically strip out the iron, and you burn off the volatile sulfur. What is left over undergoes a final process called micron-level calcination.
What happens during calcination?
Calcination at this microscopic level achieves a 99.5% decarbonization of the material. Every last trace of carbon, all the residual fuel that caused the spontaneous combustion in the black hump, is completely burned away.
So it can never burn again.
And the intense heat causes the remaining silicate minerals to expand and foam up slightly before rapidly cooling. The end result is the ceramsite pebble,
which is what Milan was holding.
It is pale, highly porous on the inside like a honeycomb, but structurally sealed and smooth on the outside.
Which brings us back to the close-pore ratio that the young chemist was so excited about. He called it a 20-kilometer stone thermos.
Yeah, that's because the inside of the calcined pebble is full of microscopic sealed pockets of trapped air. And because of that, it acts as a phenomenal thermal insulator.
Because air traps heat.
Air is a terrible conductor of heat, which makes it a great insulator. When engineers use millions of these synthetic ceramsite pebbles as the aggregate matrix to cast prefabricated concrete walls for housing, the thermal resistance of the entire structure skyrockets.
It's like building a house out of coolers.
A residential district built with these materials retains heat incredibly well, allowing the municipal winter heating grid load to drop by 7%.
The exorcism is a complete, unmitigated success. You start with an actively toxic, burning byproduct of fossil fuels that is leaching acid into the earth. You run it through this gauntlet of light sensors, X-rays and 1200-degree kilns. You rip out the valuable tech metals to fund the operation, you burn away the danger, and you are left with a premium, weightless building material that actually lowers the future energy demands of the city it builds.
It truly represents a zero-waste milestone in the clean utilization of fossil fuel byproduct. Well, for decades, the global coal industry focused entirely on mitigating the symptoms of damage. They built plants to filter the contaminated water runoff, they installed scrubbers to capture exhaust gases, they researched methods to trap carbon emissions.
Dealing with the after effects.
But neutralizing the solid waste, the billions of tons of physical gang piled up on the surface, was the final, seemingly impossible frontier in environmental remediation. And now they're doing it. You know, if we trace the lineage of material evolution we have discussed in this deep dive, the trajectory is striking in its physical logic. We began with humanity dredging ancient riverbeds, passively harvesting the naturally polished 10,000-year-old sands until the ecological collapse of the waterways forced a hard stop.
Right, the death of the rivers.
Then we transitioned to the brute force mechanization of manufactured aggregates, physically crushing entire mountains to mimic the jagged geometry required by the chemical matrix of concrete, only to realize that virgin extraction has absolute environmental limits.
You can't crush every mountain.
That realization forced the shift toward the digestive recycling of mid-century urban demolition, where the aging concrete of the city itself is pulverized, magnetically sorted, air-classified, and reincarnated as the structural spine of the next generation's skyline.
The Champa model.
And finally, we arrive at the atomic-level transfiguration of toxic coal waste, where billions of tons of hazardous, combustible gangue are roasted, stripped of heavy metals, and transformed into pristine, highly insulative architecture.
It is vital to ground the immense scale of what we are talking about here. The transition away from the sheer ecological destruction of infinite extraction is not a theoretical environmental proposal sitting on a white paper in a university laboratory.
No, it's happening right now.
It is a fully operational megatonnage reality. It is happening right now in the limestone quarries of Guizhou, in the demolition zones of Shijiazhuang, and in the rotary kilns of Datong. This relentless material alchemy is already physically holding up the skylines of the fastest urbanizing population in human history.
It's changing the physical makeup of the world.
The very definition of a resource has permanently changed. The ground beneath our feet is no longer a static vault of material to merely extract until it is empty. It is a permanent, rotating inventory of matter. It leaves you with a profound realization. If the heavy ruins of the 20th century are already serving as the active quarries for the 21st century, the very walls, floors, and foundations we are pouring today will undoubtedly be the vital, unmined ores of the 22nd.